Hello folks, we will be going over 3 examples about common large sample tests. We start with the first example. These examples, the primary reason is practice, right? This will help with these examples will help you with the assignment problems. All right, so here we start with the first example. A vice president in charge of sales for a large corporation claims that salespeople are averaging no more than 15 sales contacts per week. So he's very pessimistic about his own salespeople, and he claims that they average no more than 15 sales, no more than. Okay. 15 sales contacts per week. He would like to increase this figure, obviously, because more sales contacts means more sales. As a check on his claim, what he does is I think samples 36 salespeople, right? So we choose a sample of 36 salespeople at random, and the number of contacts made by each is recorded for a single randomly selected week. All right. The mean and the variance of these 36 measurements were 17. 17, I assume, is the mean, and 9 is the variance of this sample, right? So this sample of size 36. Let me see, what else do we have? The basic question is, does the evidence contradict the vice president's claim? It seems it does, right? So why? Because look at that. 17 is greater than 15. So when you sample 36 people, and if the average is 17, it's already kind of giving you a feeling that, hey, the claim of the vice president that each salesperson is averaging no more than 15 might be wrong. Something that can support that is the standard deviation not being too high either. All right, so we need a test with an alpha level of 0.05. Now remember that alpha is the probability of a type 1 error, meaning the probability that the null hypothesis will be rejected while in fact it was true. I think the best way would be to start with our null and alternative hypotheses. So the alternative hypothesis is clear. We think that the vice president is wrong, and we want to see if that's the case, if the claim of the vice president is inaccurate. So therefore, the alternative hypothesis is that the average, the mu, is greater than 15. So therefore, the null hypothesis would be mu is equal to 15, right? So let's just do it. So the null hypothesis is, mu is equal to 15, I guess. And the alternative hypothesis is that, nope, mu is greater than 15. The claim of the vice president is inaccurate, in fact. In our just previous video, what we did is to look into the sample, the distribution of the sample mean. We realized that the sample mean is an unbiased estimator of the population mean, right? So I'm not sure which notation we used in that video, but let's say that let's call it y bar. So y bar is the sample mean, and we claim that y bar is an unbiased estimator of mu, right? Mu is the population mean. So for us to predict the population mean, what we do is we sample some observations, in our case 36 of them, and then based on that sample we try to predict the population mean and standard deviation, right? So as a result, because of like what I said, the sample mean is an unbiased predictor of the population mean. That's what it is. And however, the sample standard deviation happens to be, and we looked at this as well, we in fact did an Excel experiment about that, is just sigma over square root of n, where sigma is the population standard deviation and sigma y bar is the sample standard deviation. Does that make sense? All right, so very good. And as a result, we are going to use, so first we need to identify the test statistic, and then we need to identify the rejection region based on alpha being 0.05, right? So therefore, let's start with the test statistic first. The test statistic is going to be the standard normal variable z, which is y bar minus mu 0 divided by sigma y bar. I think this is a straightforward one, and we can just substitute these numbers into the formula. So this is really y bar minus mu 0, and the denominator will be replaced with this expression here, sigma over square root of n. There you go. So we know our test statistic. Next, our rejection region, RR. So for the rejection region, we are going to, well, there's a couple of ways. Usually standard statistics textbooks, they come with tables, which gives us the area under the normal, standard normal distribution, right? So this is standard normal, apparently, right? If indeed you check the area, okay, let me explain what I mean. Because we are doing a one-sided test, our test is a one-sided test because look at that, mu, the alternative is mu is greater than 15. A two-sided test will be the null hypothesis mu equals 15 and the alternative hypothesis mu is not equal to 15. That would be a two-sided. In our case, we are doing a one-sided test. The rejection region will be this area to the right of, say, z here. Does that make sense? And we want that area to be 0.05. So area is equal to 0.05. So in a sense, what we are doing is we do not want the null hypothesis to fall into that area, right? So because that's a problem, and that's why we have the alpha as 0.05. Does that make sense? So the area alpha is 0.05. So therefore, the rejection region, we will only reject the null hypothesis if the z happens to, so all the observations where z exceeds 0.05, that's how we would represent. So in a sense, this 0.05, okay, let me just do it like this, 0.05. So that's what we call as the critical value. All right, so that's the critical value. And apparently, if you check table, it will give you 1.645. Well, alternatively, at the end of this video, I will, well, actually, right after this, I'm going to open Excel to show you how you guys can get it, but it's very straightforward. So you will use the norm.dist function to calculate the area to the left. But because the area to the left, the area under the whole normal distribution is 1. So therefore, if you subtract 0.05, so the area to the left will be 0.95. I think that makes sense. Sorry for that. And then, yeah, so now that we also identified the rejection region, sorry for that. Hold on. Sorry for that. Got distracted here for a minute. Now we can go ahead and substitute the values. This is a mu 0, by the way. It's not very clear here, so let me rewrite this. That's a mu. Now we are ready to find the value, the z value, to see if it is indeed, if that z that I'm about to calculate, let's just do it, I guess. See if it is greater than this. If it is, then the observation is in the inside the rejection region, and the null hypothesis should be rejected, basically. And we are very hopeful that that's gonna happen. So z is just y bar minus mu 0. I'm just rewriting this formula here. Divided by s. the square root of n, where s is the sample standard deviation. And wait, yes. So y bar came out as 17, we are told. This is y bar, 17 minus mu 0. Mu 0 is this number here. Initially it's considered that the mean is 15, and s is 9 square root of 9, which is 3, divided by the square root of 36. So if you calculate this comes out as 4 evenly. But 4 is decidedly greater than 1.645, which was the critical value, z 0.05. So as a result, the observed value of z, the z here, its observed value is within the rejection region, and as a result we reject the null hypothesis. So let me write that down. So z is inside rejection region, and so we reject the null hypothesis. We reject H0, rejecting H0 in favor of the alternative hypothesis, obviously. So at the alpha equals 0.05 level of significance, the evidence is sufficient. The evidence from those sample of size 36 is sufficient to indicate that the vice president's claim is false. We found some contradictory evidence against it, is incorrect. So basically, right, so the vice president's claim is incorrect, and that the average number of sales contacts, I should say, per week exceeds 15. Not too much more than 15, but still we have gathered enough evidence to contradict that claim made by the vice president. Okay, so that finishes the first example. Next is the second example here. Okay, so we have a machine in a factory. Must be repaired if it produces more than 10%, a ratio, 10% defectives among the large lot of items that it produces in a day. So if it starts giving a lot of defective products, then it's time to repair the machine, right? A random sample of 100 items is selected from the day's production, and it contains 15 defectives. Now 15 is about 15%, is exactly 15% of 100. So you might say, well, the supervisor says that the machine must be repaired, naturally, right? Is he wrong? Does the sample evidence support his decision? This time we're going to use a test with a significance level of 0.01. So we need to find a lot of evidence against the null hypothesis to reject the null hypothesis, I would say. So because we will be working with proportions, let me remind you that the sample proportion can be used to estimate a given binomial parameter, right? So we're going to use the sample proportion for that. And let's do it. If y represents the number of defective products, defectives, then the sample mean would be y over n, basically, right? So I mean the proportion, I should say. But before that, okay, so y is the number of defectives. Obviously y is a let's write that down here, a binomial random variable, obviously, right? Random variable. We have looked at binomial random variables previously, so you guys can check your notes over from our previous lectures if you want to. So we have a binomial variable. Actually, let's just move that down as well a little bit. Yes, there we go. A binomial variable, and a p will denote the probability of success. In that case, success being defective. So p is the probability of any randomly chosen selected item is defective. A randomly selected item is defective. I hope that makes sense. Okay, there you go, and that's it. So therefore, the hypothesis testing will have the following shape: the null hypothesis and the alternative hypothesis. The null hypothesis is that the p is at most 0.10, and we are testing this against the alternative hypothesis, which, based on the sample we have, we kind of think that that machine needs repair, right? So we are saying that at least the manager seems to say that the machine is all needs some repair, basically. All right, so this is the hypothesis test. For the test statistic, we are, like I said earlier, we are going to use the proportion. The probability will be the proportion in the sample. So test, let's write that down, statistic. It kind of, I mean, it makes sense for sure, right? So because we have a sample, the proportion in the sample can be used to estimate. It can be used as a point estimate of the population, the binomial, the parameter in the binomial random variable, the parameter p in this case, right? So in that case, p hat is equal to y over n, number of defectives inside the whole sample. And as a result, because we defined sorry, this is the p hat, right? So the test statistic itself is okay, let's just do it like this. Hold on, let me just move this down. There we go. So we are basing our test statistic based on this. Let's write it like this: based on the fact that we can estimate the probability of a randomly selected item being defective as y over n, where y is the number of defectives in the given sample of size n. The test statistic in that case would be z equals p hat minus p0 divided by sigma of p hat. And again, if you remember it from our earlier videos, that would be p hat minus p0. For the sample standard deviation, we can use the following: the square root of p0 times 1 minus p0, all divided by n. Now you need to go check your notes to remember that, but this is standard. These are commonly used point estimators. So the commonly used, just to remind you, the commonly used point estimator for the population mean is the sample mean, y bar, yeah. So and then the standard error in that case would be sigma over square root n, where n is the size of the sample. In the case of a proportion, p, the proportion parameter for the population, the point estimator for that is y over n, and the standard error is, just like we said, p success failure divided by n, the square root of that. Failure in this case is 1 minus success, so that makes sense. Of course, we can also look at some more complicated things, but yeah, we don't want it in this case. Well, or let me just remind you quickly, if you are looking at the difference between two variables, mu1 minus mu2, the estimator will be y1 bar minus y2 bar, and the standard error for that is, if I remember, it would be square root sigma 1 square over n1 plus sigma 2 square over n2, the square root of that. And finally, the difference in a proportion, so that one would be p1 hat minus p2 hat, and again, yeah, it has this long formula. Let me just write that down. For the standard error will look like this. Okay, so I just listed those commonly used point estimators for completeness sake. So this first column is the population parameters that we are trying to estimate. We estimate them based on the sample means, basically, right? And then these are the standard errors that we get along the way. We plug these into here, I should say, right? So into there so that we can get our test statistic. And once we have our test statistic, we check if it's in the rejection region or not, based on the given sample observations. All right, so let's just keep this on the side, I guess. Let's just move it a little bit like this. Okay, good. Now that we have the given ingredients, we can calculate the z, right? So z comes out, well, before the z, so let's first check the significance level is 0.01. Again, if you just check the tables, so we want to figure out, again, we are looking at the upper tail. We want to find that z critical value for which the area above z, if this is a standard normal variable where the mean is 0 and the standard deviation is 1, you can check the tables to see under what conditions this area is 0.01. You can use the binom.dist function on Excel, and z comes out as the critical value, comes out as 2.33. All right, so very straightforward. So given this critical value and given our test statistic, our rejection region will be anytime we have rejection region will be any z which exceeds z, let's call it z0, which is 2.33. So if when we plug in the values into our test statistic, if it falls into the rejection region, we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. Well, does that mean if we fail to reject the null hypothesis that the managers claim, the supervisors claim is wrong? No, not yet. For that, we need to go one step further and check the beta as well, but I'm not going to do that. All I want is, do we have enough evidence to support his decision? Let's see if that's the case. So let's first calculate the test statistic z. Z is equal to plugging in the value. So the p hat 15 defective, so 15 over 100 is 0.15 minus p0 0.10, that was the original claim, divided by the square root of success is 0.1. So we're basically estimating the denominator based on the p0s, right? And failure is 0.90 divided by a sample of size 100. So that's a square root. Actually, let me put the square root sign with a different color. There you go. The denominator is inside the square root. If you indeed calculate all this, this number comes out as 1.667. Now, it's kind of strange because when you compare it with the way we defined our rejection region, the value of z falls. We usually write this as a lowercase. When we define it, it's uppercase, but when we calculate it, it's usually written in lowercase. So z turned out to be outside the critical region, right? Our z came out somewhere here, 1.667. Do you guys see that? Less than the rejection region. Oh boy. So therefore, we fail to reject the null hypothesis at that significance level, at the significance level of 0.01. I bet we would have rejected it if, well, not I bet, I'm pretty sure, we are 100% sure, for instance, if you check our previous example, if we have used 0.05 as our critical value, then the z is 1.645. So with that, then we would have rejected it because this number is greater than 1.645. But at the 1%, with only a 1% chance of rejecting the null hypothesis, we are not that confident. But we are at least 5% confident, but not 1% confident. So we fail to reject H0 because z is less than z0, which is 2.33. Oh boy. All right, good. We kind of feel sorry for the supervisor because remember, the supervisor is complaining that the machine is not working right. And the upper management, the CEO, said that only repair a machine if you see that it creates 10% defective products. And in our sample, it created 15 defective products from a sample of size 100. That's not enough evidence to convince the CEO to repair the machine. Keep doing your job. But the reason is because our significance level is so low, right? So how can the supervisor convince the CEO? By even pulling more samples. If from 200 we found like that same ratio, 200 samples and 30 defective, the ratio being the same, then suddenly things would have changed, right? So if this number is 200, then it will be, so we would have to multiply this number by 1.4, the square root of 2. Well, the more I think about it, even that won't be sufficient. We now look into example 3. A psychological study was conducted to compare the reaction times of men and women to a given stimulus. Independent random samples of 50 men and 50 women were employed in the experiment. Obviously 50 is a large number, it's greater than 30, and so that's good for us because that's considered a large sample size. And usually in large sample size we just substitute sample values for the population values when we calculate the test statistic. The results are shown in the table below. So the table this is what we call as a 3-line table. We have 50 men, 50 women. The response time to the stimulus in average for those 50 men is 3.6 seconds for men and 3.8 seconds for women. Women slightly more time, and the mean the standard the variance, the sample variance for both men and women are 0.18 and 0.14. So given that, does that suggest, do we have enough evidence? Look at the difference, 3.6 versus 3.8, right? Does that suggest sufficient evidence for a difference between the true mean reaction times for men and women? Obviously we are going to use the point estimator, where the sample mean y1 bar will estimate the mu1, right? And y2 bar will estimate the mu2. So what is our null hypothesis and what's the alternative hypothesis? Let's directly go to the hypothesis testing. Well, this time we are looking at whether the null hypothesis, I think, is that there is no difference, right? And then the alternative is that there might be a difference actually between the average response time. So basically what we want is, we want to check if mu1 is equal to mu2, right? That's our null hypothesis. We start with that. And the alternative is mu1 is not equal to mu2. Usually, instead of writing it like this, we prefer to write this, move the mu2 to the left-hand side. So that's the same thing as this. And similarly, move the mu2 to the left-hand side. That's not equal to 0. So that is the form that we prefer to use. But now we are testing a difference of two samples. Difference of samples I already showed up above. We are going to use this one, right? The third line here. So the standard error will end up, so the denominator in our test statistic will be this expression over here. Does that make sense? Okay, so let's just quickly construct the, and obviously the significance level is to be 0.05. Okay, let's go ahead and write the test statistic. Z is equal to, like we said, y1 bar minus y2 bar minus the difference initially. We can call it d0, or you can call it mu1 of 0 minus mu2 of 0. So I just call it d0 here. So d0 in a sense is this number here, the given here. So that's the d0. And we need to divide all this by the standard error, which we decided to use that one. Mu1 square over n1 plus, sigma 1 square over n1 plus sigma 2 square over n2. That's it. So these are the most common ones that we use. The rejection region, so let's quickly write it out. Rejection region. The rejection region is equal to all the z's which, okay, so this time we need to be careful because we have a two-sided test. That's what we call as a two-sided hypothesis test. I think there's an O here, test. In the two-sided test, we have the standard normal distribution, and we want to find the area on the two tails, right? We want to make sure we only reject if the z falls into one of these two rejection regions, and we are told the area sum of those two regions is 0.05, which means the area here is 0.025, and this one as well, 0.025. So if you are using the standard, if you are using Excel with the norm dist function, so what you can do is you can calculate this z over here, or minus z, it's symmetric. So suppose you use this z over here, z0 let's call it. So you would be looking at the area to the left of this, but because the area to the right is this, the area to the left would be 1 minus 0.025, which is 0.975. So make sure you look at that value in z. If you do so, you will realize that either z is greater than z0 or z is less than minus z0. And when you look at that, you just realize that, I think, if I'm not mistaken, z0 comes out as 1.96 here, 1.96, and here this one is minus 1.96. So that's our rejection region. So let's go ahead and now calculate the test statistics and see if it falls into any of these two tails. If it falls into the tails, we are rejecting. So y1 bar, y2 bar, those are given as 3.6 and 3.8. 3.6 minus 3.8, and the difference, the d0 is just a 0, all divided by that very nasty expression on the denominator, sigma 1 square and sigma 2 square. So we can use s1 square and s2 square to replace sigma 1 square and sigma 2 square, because like we said earlier, 50 is a large enough sample. Anything more than 30 is a large sample. So it is 0.18 divided by 50 plus 0.14 divided by 50. If you finish this calculation, z comes out as minus 2.5. Now, does this number fall into any of the tails? The answer is yes. If you look at the lower tail, this value of z0 was minus 1.96, and indeed minus 2.50 is less than that critical value. And as a result, we because our test statistic fell into the rejection region at the alpha equals 0.05 significance level, we conclude that there is sufficient evidence to conclude that the mean reaction times for men and women differ. They are different. There is a difference between the mean reaction time between men and women. And that solves our third example. Hope this was useful. So this will help you with solving the assignment problems related to the some of the assignment problems related to hypothesis testing. Hope to see you guys in our next lecture.